All right, good morning, team. Good morning. I'm here to go through Unit 1, Day 3 notes, continuing on this limit journey, but talking today a little bit about limits when it involves infinity. So we're going to be looking at two cases with limits involving infinity. What happens when x is approaching infinity, and we're looking for the intended height of a function, and what happens as the limit approaches infinity at some random x in the interior of the domain. So this lesson today should feel familiar from Math 4. We're going to go through and just kind of talk about case 1 first, which is the limits as x approaches a positive or negative infinity. Okay, so looking at these functions that are down here, we're going to try to determine together what the limit as x approaches infinity would be. Okay, so now we're imagining x being infinity means that we are way far down the horizontal axis. So we are at the edges or the ends of the graph. And we're saying if the graph were to theoretically end, what would the intended height of our function be? Last year, I think you referred to it as end behavior. So looking at this first function f of x, I'm going to think to myself, what would happen if I plugged in an enormous number? Well, this function is a little complicated, so what I would rather do is figure out like a simpler function that could help me kind of determine what the end behavior was, and I'll kind of show you how I do it. It's called an end behavior model, so I'm going to call that end behavior model, okay? So the end behavior model is going to be a simpler function that behaves the same as f of x at the ends. Now, this simpler function and f of x have nothing in common at the rest of the graph. So at x equals 3, they have nothing in common. At x equals 0, they have nothing in common. At x equals negative 100, they have nothing in common. But at x equals infinity, they're going to have something in common. And so here's the process of finding our end behavior model. If I look at just the top and I'm focusing on the top, if I'm going to infinity, let's say, and I plug in infinity, if I have infinity dollars and you try to give me $1, I'm going to tell you to keep your dollar. This little positive 1 has no effect on this graph or very minimal effect at a really, really large number. So I'm going to pretend like it's not there. Same with negative 5. Okay. Now you're like, all right, I can buy that. But let's talk about this x cubed. 5x cubed versus 4x squared. Let's think about plugging in just the number 1,000, okay? If you square 1,000, you get 1,000,000. So if I put 1,000 in here, I get $4 million. I like doing it in dollars because that makes more sense to me. Okay, if I put 1,000 here in for x, I get $1 billion. So $5 billion minus $4 million. So if I have $5 billion minus $4 million, I still have $496 billion. So although at x equals like 1, these two things are basically the same, at x equals 1,000, there is a big difference between 5x cubed and 4x squared in its value. And if I plugged in something like 1,000,000, it would just get even worse. 1,000,000 cubed is way bigger than 1,000,000 squared. So as we get larger and larger and larger, this squared term is going to have less impact than this cubed term. So I'm just going to kind of say, okay, at the large number, that doesn't make any difference. So if you look at what's on top, the only thing that had the biggest influence or the biggest impact when I plugged in 1,000,000 was this 5x cubed. Now the same argument could be applied to the bottom. So if I look, squaring 1,000 versus, this is trillion. If I plug in 1,000, guys, this is a trillion. And this is 1,000,000. If I had $2 trillion, okay, and I added $3 million, you're like, yeah, that would be nice. But like, I have $2 trillion. What's millions when you got trillions, okay? So that wouldn't be. So my end behavior model is just going to be that little fraction that's left. And again, this fraction has the same behavior when we're talking about plugging in infinity. It does not have anything that is the same anywhere else on the graph. Now, if I look at this little simpler function, an easier function, I can actually reduce that because 3 of these x's would cancel and leave me with 5 over 2x. So this little function is my end behavior model. And so I'm thinking to myself, okay, whatever this function does, f of x will do at infinity. So now if I imagine plugging in infinity to this function, okay, the simpler function, I would get 5 divided by 2 infinities. $5 divided by 2 infinities means everybody's poor, okay? A small number divided by a huge number is going to be basically 0. Even if I plug in negative infinity, that's still like 5 divided by negative infinity. Like that's a really, really tiny number. It's negative, but it's still basically nothing. So positive nothing or negative nothing is still just nothing. Okay. Let's go on to the next one. So if we look at g of x here, again, I'm only talking about really large x's. So I'm only going to focus on the simpler function, the end behavior model, and I'm going to imagine what that function does. And even if I were to think about like the graph of 5 over 2x, the graph of the 5 over 2x looks something like this. So I can see as I went to the infinities, we were going to heights of 0 there. Okay, this one, if I look at the top, the biggest influencer is this negative 2x cubed. If I look at the bottom, the biggest influencer at infinity is going to be 3x cubed. Now, if I simplify that fraction, I get negative 2/3. So if I think about that function y equals negative 2/3, if I were to graph it, y equals negative 2/3 is a horizontal line at a height of negative 2/3. So I can use the fact that this function here has the same behavior as g of x at infinity. So if I wanted to look at infinity, if I have a constant, its intended height is the same everywhere. So at infinity, the intended height of the simpler function is negative 2/3, which means the intended height of g of x will also approach negative 2/3. Okay, same with negative infinity. A constant has the same limit everywhere because it has the same height everywhere. Okay, you're like, all right, this is feeling familiar. I'm remembering this from last year. Now, if we do this one, we have x squared plus 2x plus 1 on top if I distribute it out over 2x squared. So now if I want to come up with my end behavior model, again, I'm just focusing here on the things that have the biggest influence. So x squared, and the bottom's nice because it's only one thing. So I'm going to have x squared over 2x squared, which if I reduce that model, I get y equals 1/2. So again, that's just a constant function. Now, does k of x look like the little graph I just did? No, k of x is going to probably look something like this. Okay, it's going to have some asymptotes. Maybe it looks like this. Like, I don't know exactly what it looks like, but I know that at the edges of that graph, they have the same intended height. So if this intended height is 1/2, then our limits on both sides would be 1/2 because it's a constant function. All right, do some more. All right, so now let's focus on an end behavior model for h of x, okay? So I'm going to take 2x to the 4th over 3x cubed because they're the biggest influencers. Again, this function, I'm only taking the largest ones because we're plugging in really big numbers, and like 16 is not going to have any effect on a really big number cubed, okay? So that's why we're kind of ignoring that. And now if I simplify it, I get 2x over 3. Or I could write that as 2/3 x. So 2x over 3 is the same thing as 2/3 x. So if I think about that graph, it looks like this. Y equals 2/3 x would look like that. So if I'm looking here, if I'm going towards infinity, this function is going up towards infinity. The limit would be infinity. On the left side, the function is going down towards negative infinity. So the limit would be negative infinity. So you can either think about the graph of the end behavior model, or you could plug in infinity into the simpler function and think about what the answer would. 2/3 of infinity is just infinity because it's still a really big number. 2/3 of negative infinity is still negative infinity, okay? If I have trillions of dollars of debt to China, like we do, and they're like, you know what, we're going to give you a discount. You only have to pay 2/3 of your hundreds of trillions of dollars. We're still having to pay a lot of money. Okay, j of x. Now this one is a little bit harder than the other ones, so let's just talk about an end behavior model here. If I'm talking about an end behavior model, the top is nice because it's just an x. The bottom at infinity, now remember I'm only looking towards infinity, that 1 is going to have no influence, so I just have the square root of x squared. Now here's where there's a little bit of a catch when it comes to this function, because the square root of x squared does simplify, but it doesn't simplify into x. It simplifies into absolute value of x. So if you remember from Math 4, all those years ago when you took Math 4, okay, let's say I took the square root of 2 squared. If I square 2, I get 4, and the square root of 4 is 2, okay? Let's say I take the square root of negative 2 squared. Well, negative 2 squared is just 4, and the square root of 4 is 2. So you can see here, when we had the same expression with different sides into that square root of x squared, we ended up with the same answer. So there's like a plus or minus situation that happens with the square root of x squared, hence why we have absolute value. Now, this graph should feel familiar because we just did it last class. This is our step stool graph. So if you think about the graph here, okay, I know that the right side of this graph is 1 and the left side of this graph is -1, and they're constants, so I know the right is going to 1 and the left is going to -1. Now, if you're not sure about that, you're like, I don't trust it. Okay, well, remember that absolute value is a piecewise, right? So if absolute value of x is a piecewise, on the right-hand side, I can treat that as x over x, which would simplify into 1. On the left-hand side, absolute value of x is the same thing as negative x, which if I simplify that, I get y equals -1. So here are simpler end behavior models in terms of the piecewise that is, or you can just remember what the step stool graph looks like. Okay. Let's do one more, and then we're going to summarize this. So here, I can't come up with an end behavior model. It's not possible. Okay, so what I have to do with this situation is kind of imagine to myself plugging in infinity. So if I imagine plugging in infinity, this is a composed function. I can see that this is a function inside of a function. So I'm going to evaluate it from the inside out. So if I'm thinking about x approaching infinity, that means that this value down here in the denominator is going to be approaching infinity, and 1 divided by infinity is approaching 0. So this just becomes the cosine of 0. Now, if I think about my unit circle, 0 radians is over here. Okay, the cosine of 0 is 1. So that limit would be 1. Now, if I imagine plugging in negative infinity here, okay, 1 divided by negative infinity is basically -nothing, which is the same thing as saying nothing. So we get 1 on both sides. Okay, so whether you're plugging in infinity or thinking about the graph of your end behavior model, it'll help you get the limits every time. Now, I will tell you in Math 4, you kind of learn this a little bit backwards. So I'm just going to talk about like what we're finding here. So if the limit as x approaches an infinity equals some value, that's a constant, or the limit as x approaches negative infinity of f of x equals some constant, then we can conclude that y equals b is a horizontal asymptote. So last year in Math 4, you guys decided that there were these horizontal asymptotes that you found using these rules, and then we described them using limits. It's actually the reason why something is a horizontal asymptote is this part. So this is the y and this is the what. So if I ask you, what is the horizontal asymptote? You would be like, the horizontal asymptote, for instance, for number 6. Let's go for number 6. Does this graph have horizontal asymptotes? Yes, there's a horizontal asymptote of y equals 1 because the limit as x goes to infinity of m of x is 1. Okay, or you could say the limit as x goes to negative infinity of m of x is 1. For instance, j of x. Does j of x have horizontal asymptotes? Yes, it has 2. Y equals 1 is a horizontal asymptote because the limit as x goes to infinity of j of x is 1. Y equals -1 is also a horizontal asymptote because the limit as x goes to negative infinity of j of x is equal to -1. Okay, so the reason why, if I asked you to justify, is because it's a limit. Now, rules of thumb for rational functions. These are kind of like what you learned last year to how to determine if a function has a horizontal asymptote, but I just kind of want to generalize it to fit any situation. So here are the 3 cases for rational functions, so fractional functions. The first case is top-heavy. Okay, top-heavy functions means the top grows faster than the bottom. In polynomials, that meant the degree is higher, but we can mix exponentials with logs, with sines, like we can mix them all together. So you're just thinking the top grows faster. When the top grows faster, the limit as x approaches one of the infinities is an infinity, okay? And the way I imagine this, a top-heavy function means the top is going to be way bigger than the bottom. If it's shaped like this in its growth, it's not going to be able to stay upright. It's going to tip. That's like saying we have a woman that has like nothing, like chicken legs, okay, and huge knockers. If that's the case, that woman is going to tip over. Like her, she's going to have tons of back problems. She's going to be walking with a cane when she's 80. Like a top-heavy function tips, and it's going to tip going towards infinity, or it's going to tip going towards negative infinity. So top-heavy functions tip, which means their limits would be infinity. In turn, that means there's no horizontal asymptote. The next case would then be bottom heavy, and I'm going to define bottom heavy as the bottom function grows faster. Okay, if the bottom grows faster, then we have a shape like this for the function. The bottom is getting really big, and the top is getting not so big. Okay. This is like a woman that has nothing on top and is thicker than a Snicker on the bottom, okay? She's dragging to the ground. Gravity is not that lady's friend. Everything's going to be sagging by the time she's 80 years old, okay? She's going to be just drooping. And when that happens, everything goes to the ground, and the limit as x goes to one of the infinities is 0, which in turn means the horizontal asymptote is y equals 0. Now, the third case, my darlings, is what I like to call Beyonce, because Beyonce is perfect in every way, okay? She is on point. She will be perfect forever and always, no matter how much time goes on. A Beyonce function means that the top and the bottom grow at the same rate. That would be a function that looks like this. Your perfect hourglass shape, okay? If that's the case, whatever this proportion is, this ratio is, that's what your limit is going to be. So here, the limit as x goes to an infinity is going to be the ratio of coefficients. In this case, you will also be able to recognize, because if you found an end behavior model, you will always end up with a constant in a Beyonce case. Okay, so it's top heavy, bottom heavy, or Beyonce. So here's what I want you to do. I want you to pause me, and I want you to go through 7 through 11 and try to find those limits. And then when you're done with finding all of those limits, unpause me and come back, and I'll go through the answer. Okay, welcome back. So if we take the limit here, I can see that I have a squared on top and a squared on bottom. That's a Beyonce. So it'd just be 1 over 1, which is just 1. Okay, so I can think here my end behavior model would be y equals x squared over x squared, which is just y equals 1. It's a constant. That constant would be the limit. Okay, number 8. Now this one is a little tricky because it has a 5 minus. But if you remember from last class, limits have properties. So what we could do here is we could just split this up, because there's subtraction, into the limit as x goes to infinity of 5 minus the limit as x goes to infinity of x squared over x cubed plus 6x, and treat it like two separate limit questions. If that's the case, the limit as x goes to infinity of 5 is just 5 minus. Now this limit, I'm going to have to think about my growth. I have x squared on top and x cubed on bottom. It's bottom heavy, which means it'd be approaching a 0. You can also think, what would the end behavior model here be? The end behavior model would be x squared over x cubed, which is just 1 over x. And if I plug in infinity, I get 1 over infinity, which is 0. Same thing with the right side. It would just be 5. Okay. Now 9, this is our step stool function again. The only difference is that this step stool function is at 2 and negative 2. Okay. So I know the limit as x goes to the right is 2, and the limit as x goes to the left is negative 2. Again, if you're like, I don't know, then treat absolute value like a piecewise. On the positive side, absolute value of x is just x. Those x's would cancel and leave me with 2. On the left-hand side, absolute value of x is negative x. And so if I plug that in, I get negative 2 as the function, and so therefore that's the limit. Okay. 2 more. Now the next one. Notice that I mixed a linear function with an exponential function. So for this one, I'm going to graph them on the same coordinate plane so you can see. But this is kind of what I end up with. So if I'm thinking if I see the limit as x goes to infinity, that's like, is this a Beyonce case? So I just think infinity and Beyonce, they all go together. Okay. Now, if I'm looking at this, on the right side of this graph, I'm asking myself who grows faster. Would it be infinity or e to the infinity? Well, if I'm looking at my graph, e to the infinity would be larger because e to the x grows faster. So this is bottom heavy and it'll approach 0. The left-hand side here, now the left-hand side gets interesting because if I look at the left-hand side, the steeper function is actually y equals x. So on the left-hand side, this would be top heavy. If it's top heavy, then I know the answer is going to be an infinity. And so I just have to figure out which it would be. So if I look at plugging in negative infinity, this would be negative infinity over e to the negative infinity. So that's a big negative divided by a small positive, which is going to equal a big negative. So the answer here is going to be negative infinity. So again, when it's top heavy, you know the answer is going to be an infinity. It's just a matter of figuring out, is it positive or negative? Okay, last one of these. So now in this next one, I'm looking at this function and asking myself here, is it top heavy, bottom heavy, or Beyonce? Because I see this, okay? Now, I know earlier we were like the limit of sine of x over x is 1. Like that was something that I was like, you should know that one. We graphed it. Look at that. But remember, that's the limit as x goes to 0, not the limit as x goes to infinity. When it's infinity, it's asking for end behavior. So if I think about it, sine goes like this, and y equals x goes like this. Okay, so if I'm talking about at this edge of the graph, no matter where I stop on sine, that will always be smaller or a lower value than what x is at infinity. So in this case, it is bottom heavy and it would be 0. Okay, so that's a little bit about the first case when x goes to infinity. I'm going to keep moving along and talk about, okay, what happens when the limit, if I have the limit as x goes to c somewhere in the graph and the intended height is infinity. Okay, so now there's a couple of ways we can do this. We can come from the left. So if I have x going to a number and the answer is infinity on a side, or from the right and it goes to one of the infinities, I'll put a plus or minus, could be either. Okay, then what's happening is that x equals c is a vertical asymptote. So that's what I have here. Now, if you're like, how am I going to know? Well, I'm going to give you a problem like this, okay? And you're going to be like, I'm going to plug it in because I know that's what Ms. Bowman said to do. And I plug it in and I get a number over 0. This is your alarm that there is a vertical asymptote. Okay. So that should be like the ding, ding, ding in your head, and we have a vertical asymptote. Now, this is where it gets a little bit tricky because that is a non-existent number, which means the limit does not exist. But if I think about graphs, I could have vertical asymptotes that look like this. Okay. I could have vertical asymptotes where the graph looks like this. And I could have vertical asymptotes where the graph looks like this. All three of those cases, when I plug in, I'm going to get a number over 0 for the limit. But if I look at this graph, it looks like both sides are going up towards infinity. So when I write this limit as x approaches c of f of x, I'm going to say that that limit equals infinity. Now, infinity is not a real place. Even though they're going to the same place, their location is an imaginary world. They're going to Narnia, guys. So like, even though they're both going to Narnia, Narnia is not real as much as we would like it to be. So this limit is a non-existent limit. but the way I'm describing it is a very specific way to describe the DNE, because we're saying, like, although it's not going to a real place, I can tell you both sides of the graph are heading towards infinity, and that'll at least allow you to picture it in your head. Same with the second graph. If I find the second graph, I can see that both sides are going to the same Narnia. Okay, so I'm going to describe that Narnia. Now this one, okay, when I look at this graph, one side, the left limit is going to infinity, and the right limit is going to negative infinity. So in this case, I'm just going to have to say the limit does not exist. All three of these are does not exist limits. And if you were to plug in C in all three cases, you would get a number over 0, which means for us, when we get a number over 0, we really have to figure out which which vertical asymptote case is it? Is it case A, case B, or case C? So I'll call this A, B, C. Because if it's case A and I get a number over 0, I want to write it as infinity. If it's case B and I got a number over 0, then I want to write it as negative infinity. And if it's case C, the only way I could write it is does not exist, and I'll be safe. So if you just put does not exist and move on with your life, the only time you'll be actually accurate is with C. And the best way I can use to describe this analogy is to say, look at this shape, classify it. If you told me this shape was a rectangle, I would say you're absolutely right. All three of these cases are rectangles. But if you look, is there a more specific way to describe this rectangle? Yes, it's also a square because all four sides are congruent. Saying these two cases here is calling something a square. And we want to be as specific as we can be when we're doing these problems, because it's just going to help us communicate behavior and what's happening in the graph. So we'll do a couple of examples finding vertical asymptotes, and then we'll call it a day. Okay, so here in my first example, how do we find vertical asymptotes of a function? So here's what I want to make sure that you understand. There are 3 steps: factor, simplify, and then set the bottom equal to 0. Sometimes we have holes in graphs, so it's important that you do these 2 steps to make sure you don't miss any holes. So I'm going to factor f of x. When in doubt, always factor out. Okay, so it factors into this expression. I can see that nothing cancels, which means nothing would be a hole, which means I have 2 vertical asymptotes. I have a vertical asymptote at 3 and a vertical asymptote at x equals -2. So those would be the vertical asymptotes of the graph. Now, that means if I were to find the limit as x approaches, let's say 3, okay, and I plugged it into this original function, I would end up with 6, and I'm using this form just so you know because it's easier for me to do, and then 5, and then 0, and then 5. Okay, I end up with 30 over 0. So in my heart, I'd be like, oh, the limit doesn't exist because I have 0 on the bottom. But again, this is like a ding, 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 that this is a vertical asymptote. And I have to figure out in this vertical asymptote, which case do I have, A, B, or C? So when this happens, and if I did the same thing for -2, I would also get a number over 0. So what you would need to do is investigate the behavior of f around these asymptotes by finding the sided limits. Okay, and that'll tell you if you have a case A, a case B, or a case C. Now, as I'm testing the behavior, I already know there's a vertical asymptote in this graph, which means I know that every side is either going to be going towards infinity or negative infinity by definition. Okay, so since there is a vertical asymptote, I know the one side limits are infinities. So I actually don't really care about what value I get when I investigate the behavior. I'm just going to look and test a decimal that's just to the left of -2 so that I can decide whether or not the left side is going up towards infinity or down towards negative infinity. So here, if I take this and I test a decimal like -2.1, watch your negatives because it works backwards than what you're used to. What I'm going to do is I'm going to plug -2.1 into my function, and all I care about, team, is the sign. I do not care about the actual value because I'm not trying to multiply and add some decimals. So if I do 2 times negative 2.1, I end up with a negative factor. If I do 2 times negative 2.1 minus 1, I end up with a negative factor. If I do negative 2.1 minus 3, it's a negative factor. I don't care that it's negative 5.1. I just care that it's negative. Negative 2.1 plus 2 is a negative factor. So if I look, I end up with a positive numerator and a positive denominator, which means the answer would be positive. Since I know the answer is positive and I'm just to the left, I know it's going to positive infinity. Okay. Don't go to negative 3. I know you want to go to negative 3, but you have to stay close. Going to negative 3 is like trying to jump over the Grand Canyon. Like there's so much that happens between two integers that you want to make sure you pick a decimal that's close. As annoying as testing a decimal is, I'm going to plug a decimal that's close to negative 2. So like negative 1.9. So negative 1.9 times 2 is negative. Negative 1 times 2 minus 1 is negative. I get a negative, and then I get a positive. So here I can see I have a positive on top, a negative result on the bottom, which would give me a negative result, and therefore that behavior is negative infinity. So then if I wanted to describe the limit in general, because the infinities are the same, the only thing I could say is that the limit does not exist. If they would have both been positive infinity, I would say the limit as x approaches negative 2 is infinity, or likewise if it was negative. Now to save myself some breath, if I were to do 3 here, I'm going to test decimal 3, just to the left would be 2.9. So if I test 2.9, I get positive. 2.9 times 2 minus 1 will definitely be positive. 2.9 minus 3 would be negative. 2.9 plus 2 would be positive. I end up with a negative, which means the answer is negative infinity. If I test 3.1, I'm going to end up with all positives, okay, which tells me that my answer would be positive infinity. So again, if I ask for the limit as x approaches 3 of f of x, the only thing I can say is that it does not exist. Okay, so some tips and tricks. Use decimals close to your vertical asymptote. And then the other thing I'm going to say is plug into your factored form. And then just a reminder, if you get a number over 0 in your limit, that usually means there's a vertical asymptote. If you get 0 over 0 in your limit, that means there's a hole, okay? It's two different situations that you need to recognize because the process of how to handle it is different. So why don't you guys try to find these two limits? Okay, so pause me and then unpause me and I'll go through the answer. Okay, so this first one. If I plug in negative 3, I get 1 over 0. That's, again, my alarm. There must be a vertical asymptote. Now, if you know that this graph is 1 over x just shifted over 3, and you're like, Ms. Bowman, I already know what that graph looks like good for you. You know the infinities are different, so you're just going to tell me the limit does not exist. If you don't know what this graph looks like in your head, then that's not a problem. You're just going to have to find the limit as x approaches negative 3 from the left, and the limit as x approaches negative 3 from the right. Okay, and again, since I got 1 over 0, that's my clue that there's a vertical asymptote, which that means that the one-sided limits the answer needs to be infinity. So if I plug in something to the left, like negative 3.1, I end up with a negative, so it's negative infinity. If I plug something in here to the right of negative 3, like negative 2.9, I end up with a positive, so the answer is positive infinity. So the limit does not exist. Okay, same thing here. If I were to plug in 5, I'm going to get negative 4 over 0. So that's, again, my clue that I have a vertical asymptote. So now I'm going to find the limit as x approaches 5 from the left, the limit as x approaches 5 from the right, and I'm going to go ahead and factor this because when in doubt, always factor out. It just makes your life a little easier to test if you have it in factored form, especially because you need to be plugging in decimals that are close. Okay, so if I plug in, let's see, I always have to do this. To the left is 4.9, so I have a negative on top. 4.9 minus 2 is positive. 4.9 minus 5 is negative. I end up with a positive, so that limit would be positive infinity. If I go 5.1, I have a negative on top. 5.1 minus 2 is positive. 5.1 minus 5 is positive. I end up with a negative, so this limit would be negative infinity. What that tells me is that the general limit does not exist. So we'll do two kind of tricky ones. Tangent is a graph that you should recognize, okay? So if you know that this looks like this and that this is pi over 2 right here is the asymptote, you know it's going to infinity. If you didn't, let's go ahead and do an algebraic way. So if I plug in tangent of pi over 2, and I'm thinking about my unit circle, pi over 2 is 90. The quadrantal point is 0, 1. Tangent is the sine over cosine, so it'll be 1 over 0. So again, this is my clue that we have a vertical asymptote. Now they only want us to come to one side, so since I know it's a vertical asymptote, I know the answer is going to be infinity. So what I'm going to do is I'm going to test a point, okay, that's just to the left of pi over 2. So if I'm thinking here's 0, here's pi over 2, I want to pick something over here that's between 0 and 90. I can do any angle that I want between 0 and 90 or 0 and pi over 2. So maybe I do pi over 4, okay, or 45 degrees. And I'm just asking myself, is it positive or negative? That answer is positive. So the tangent of pi over 4 is positive. So that means my limit would be positive infinity, which again, if you know the graph, then you already know the answer. But if you don't, you have a way to do it. And just to remind you from Math 4, if you want to remember which trig identities or which trig ratios are positive, it's I did a small tasty cookie, or all students take calculus. All are positive, sine is positive, tangent's positive, cosine is positive. Okay, let's do this last one. The limit of x approaches 3 from the right of ln of x plus 3. So if I go ahead, oh, this should say negative 3. I think it does in your notes. I'm hoping. Okay, so if I plug in negative 3, I get the ln of 0, which does not exist. Okay, so then I'm going to say, okay, I want to test a point that's just to the right of negative 3, like negative 2.9. So if I take the ln of negative 2.9 and I plug it in, I get the ln of 0.1. So since this is a decimal, e can only become a decimal on the negative side, so I know this answer is negative. So this would be negative infinity. Now, again, if you know what ln looks like, okay, this ln graph has been shifted over 3, it would look like this. If you know that graph, then you know that limit is negative infinity, and you wouldn't have to go through all the problems of testing it, okay? But that's all I got for you guys. So on that note, enjoy.